Thank you. Yeah, so it's a great pleasure to be here today. Also, I'd like to thank my postdoc, David Andrade, who's now gone on to a faculty position in Colombia. So it's been a great pleasure to work with him on some of the things that I'll be talking about. So the title is you can see the title. It's quite long. I want to talk about instabilities from a kind of a practical perspective. And so when I think about instabilities, in particular, these kinds of classical deep water wave instabilities, I'm thinking, sorry, let me use the mouse here. Thinking that we are generating waves. We try to generate some waves. Here are some experiments by Bonnefoy and et al. In JFM. So you generate, say, mother waves 1 and 3. And you can see them here in the flume in Central Nantes. And when you generate them together, actually something unexpected happens, which is a bit difficult to see. You kind of have to squint or believe what they tell you here. It's that there's a daughter wave or a child wave that's going that way. So you're trying to generate waves, and this is, of course, is a well-known setting, and you get something slightly different. And the best known scenario where this occurs, of course, is Benjamin Fair instability. And we've heard a lot about this today already, and I think we'll hear more about it tomorrow. And so this talk is really about the classical setting of Benjamin Fair instability, and hopefully I'll provide a bit of a new perspective on that. So Benjamin Fair, and now we're here, and this is frequency, and we've got Fourier amplitudes. So we think that we're generating, or we'd like to generate, a single wave, so a periodic wave train, Stokes wave, for example. But there's some noise, and then what happens down the tank is that some of this noise is preferentially amplified. In particular, in Benjamin Fair, it's those sidebands that come up and grow. And so this is why it's difficult to generate Stokes waves in the wave flume, and people have recognized this for 60, 70 years now. So what's the classical kind of setting to go and understand this? Well, the setting that Stokes used himself, to go back to 1847, is really perturbation theory. You're looking at the weakly nonlinear problem, so you're assuming, and now I'm cognizant because of where's the chalk? Is it over there? So because not everybody here, it's a very diverse audience, not everybody here is working on waves. So I'll do at least a quick sketch. So this is can anybody see this? Yeah. So I have an amplitude that's always going to be A. I'm going to take the wavelength, which will be, say, crest to crest, lambda 1/k. Right, and my free surface is going to be zeta. Later on, maybe I'll put down my small parameter here. So in this weakly nonlinear theory, right, we take potential flow. So I've got, say, a Laplace equation and my combined boundary condition. If I linearize, which is what people were doing in the 1830s, you get these solutions. So I'm not writing down what the amplitude is. It's not really relevant. E to the plus minus I kx minus omega t. And so this is the leading order. And then you go to the next order if you I don't know, have Maple or are patient like Stokes was and other people were. And then what happens with these lower order solutions is that they appear as inhomogeneities, right? So you've got the free part, and then you've got inhomogeneities in your system. And at the second order, those inhomogeneities are, let's say, quadratic terms in your linear solutions. So if I take a linear solution that looks like e to the plus minus I kx minus omega t, the inhomogeneities are products of those. So, and then in the exponential, that sums together. And then you're looking for, okay, so when is something exciting happening? Well, usually when you've got inhomogeneities on an equation, it's exciting when the forcing has the same frequency as, say, a free solution. So in this case, we've got frequency and wave number. So we've got resonance in this problem if on the left, I've got a frequency and a wave number, and on the right, I've got two of them here with pluses and minuses. I haven't written all the plus minus signs just to keep the notation simple. Now, if I go in order higher, so epsilon squared, okay, you repeat the kind of same game, but on the right-hand side, I've got these three terms in the inhomogeneities, and I get resonance if something like this is satisfied. And I need to make sure that, well, satisfying this means finding wave vectors, say K1, 2, 3, and 4. These are the quartets that were just being discussed. And so we're thinking about wave vectors 1, 2, 3, and 4, for example, that will satisfy this condition with pluses and minuses, if you like. But of course, you also need to satisfy this condition on the omegas. And as it turns out, if you're in deep water, dispersion relation tells you how omega and K go together. And these guys, so the triad resonances are excluded. Right, so this is the answer to why Stokes, when he was doing perturbation expansion, couldn't stop at second order. Right, so Stokes, he was going and going, I assume, and then second order, he didn't find anything exciting. So unfortunately, he had to go to an order higher. And then suddenly, things happened. Why? Because there's no resonance at second order. So you've got to take the cubically nonlinear bit of the equation. So, of course, it's okay to write down for a single mode, but then once you have multiple modes, it's really a hassle to do the perturbation theory. I mean, really terrible. Except, well, maybe with computer algebra. Even then, I don't recommend it. But there's a good, concise description that you can get from the reduced Hamiltonian formulation, which I'm taking now from Krasicki in 1994. So this is basically the water wave problem up to third order in nonlinearity, where we've transformed into Fourier space, and I've discretized Krasicki's Hamiltonian because that's the form that I'm going to use. So the Hamiltonian here looks like this. It's written in terms of complex amplitude, complex B's that are related to Fourier transforms of the free surface elevation and the potential of the free surface. And it contains, well, so here's the relationship. If you want to get back from the B's to the free surface, here in the discrete formulation, you do this sum, and it gets you back to where you want to be, zeta as a function of x and t, for example. The resonance condition, so between these quartets, 1, 2, 3, 4, is encapsulated in a Dirac delta right here. And then the omega I is a linear dispersion relation in water. And then all of the ugly stuff is encapsulated here in this, this term, which looks innocuous, but is really terrible. Yeah. So the term is algebraically very, very lengthy. So this is the kernel that you get out, or that Krasicki gets out. Plus minus a few typos. If you find some new ones, please tell me. But no, up to third order, it's fine. I think also fourth order is okay. But so this kernel term makes this not a completely generic equation, right? That's where the water wave stuff is hidden. So, okay, what does this equation have to do with the water wave problem that we've been discussing? Well, okay, since we've got a Hamiltonian and it's discrete, we can look at equations of motion. And these equations of motion are really the discrete form of the Zakharov equations, right? If I look at my Hamiltonian, well, the equations of motion corresponding to that, here's the Zakharov equation. If you imagine this this sum to be a triple integral and the Kronecker delta, Dirac delta, there you go. It's the classical Zakharov equation. And it's also, people don't really like it so much, mostly because of the kernels, but in simple cases, it's not too bad. So if I assume that there's one mode only in the whole C, so all of these sums, so there's only one index here, the equation boils down to this guy right here. This is the equation. And you can solve that equation for a constant amplitude. And then invert, you get back, using the sum that I showed you, get back to the free surface elevation zeta. And out pops Stokes waves. Right? So it's what you would expect, because I said it a little bit ago that this whole formulation is the water wave problem in Fourier space truncated at third order in nonlinearity. and throwing out the non-resonant terms. But I won't talk about that today. Yeah. So here's Stokes wave. Yeah, that's you get it out of the formulation quite naturally. And if you do two modes, all right, you've got two ODEs, fine. You can solve them again, constant amplitude, and it's Longet, Higgins, and Phillips. They had to work hard using perturbation theory to get these two, this bichromatic C. But with the Zachara formulation, well, the work is done. Just solve this system, and out pops the mutual frequency correction solution of Longet, Higgins, and Phillips. And we've heard about it today, and I'll make one kind of, it's a slightly illegal jump, and I won't justify everything. I say in the continuum limit of this Zakharov equation, something has gone wrong here in my slide. Sorry, this clearly when I copied this over, the text moved around. So if I expand, if the energy is concentrated about a single wave number, that should say K0, and I expand the dispersion relation about it, and I approximate all the interaction coefficients by the interaction coefficient of the Stokes wave. Let's see if the, okay, and I rewrite using an envelope amplitude, I get a Davies-Stewartson equation. So this is, as long as this equation is displayed, that's the main thing. Yeah. All the other stuff, this is the process that you take. And that process is, the Zakharov equation is a broad-banded mother equation to NLS. I mean, that's 1968, Zakharov, and also to Davies-Stewartson, if you like, and also to higher order NLS equations, right, shown by Stiasny and Schemel in the 80s and so on. So we can make some comparisons with NLS, and I will in a few places. Yeah, so hopefully there will be some tie-ins to Anisa's talk a few minutes ago. Okay, so well, where is Benjamin Fair instability in all of this? So we've seen that we can get systems of ODEs for the Stokes wave, for a bichromatic C. So what system gives us Benjamin Fair instability? Well, it has to be some kind of quartet. Remember that all of everything that we're doing now has to satisfy this relationship. And the Stokes wave is just 1 + 1 = 1 + 1. It's a trivial kind of resonance. Bichromatic is 1 + 2 is 1 + 2. The next simplest is what's called the degenerate quartet, which is this is the really first non-trivial energy exchange that you can get. Yeah. So I've got two copies of wave A is equal to wave B plus wave C. So I'm thinking about those wave vectors over there, although I'm mostly going to be showing you unidirectional results. You can change this and you can do it for directional cases. So the system of ODEs that you get, okay, unsurprisingly, 3 ODEs for A, B, and C. These guys are nonlinear frequency corrections. I won't write out, it doesn't make sense to write out all of this stuff. This is basically what you saw for the Stokes wave right here. And pointer has given up. Okay, so the usual approach that goes back to the 1980s is to say, let's assume that one of these modes, say wave A, is much bigger than the other. So I'm going to linearize this system of ODEs. Okay. Interesting sounds coming from the PC. So I'm going to linearize the system of ODEs here, assuming that A is my carrier. So the carrier, it starts off big, and then the other modes B and C are maybe small. So yeah, that's fine. No, still not working. The first equation is just the equation for the Stokes wave that we saw before. We can solve it with constant amplitude for BA. And then the other two equations are uncoupled. They're a linear system, and I get basically an eigenvalue condition for when I've got instability. So this is the kind of thing that Crawford and Crawford, Safman, and Yen were doing. Yen and Lake have this in the early 1980s, looking for the Benjamin Fair instability condition from the perspective of the Zakharov equation. And for the NLS aficionados here, if you take the narrow bandwidth limit of all of this stuff, which you can do, it boils down to this NLS instability criterion, where epsilon says here, epsilon is AK. I'll just write it down here, is AK. And my modes, so I'm going to use this mode separation picture little bit. So if this is Ka, then this is Ka plus P, and this is say Ka minus P. Yeah. So it depends on mode separation P and on the steepness epsilon. So this is the classical result, and it gives you this kind of stability region in terms of mode separation P and epsilon, where you see, okay, for actually it never restabilizes here. And yeah, well, you've got basically this linear criterion. This is NLS. The Zakharov equation, which is the broader bandwidth generalization, gives you this horn. You might recognize if you've been reading papers from the 80s. This instability horn, of course, it matches NLS where the bandwidth is small, but it has some restabilization features for large steepness, and there's an interplay between the steepness and the mode separation. I'll come back to this picture in a little bit. So far, it's all classical. Now, what else can be said about this problem? So we've linearized. And ask ourselves, is the linearization any good? And what happens after the initial linear growth? Because we know clearly the assumptions of the linearization are invalidated. And I think there's a really simple but transparent way to answer this question. And the way is to look at the conserved quantities of the system. So we've got momentum, which is conserved. So here it's Ki times the modulus of the amplitude squared. Wave action is conserved. And of course, we've got the energy as well, the Hamiltonian. The first two don't involve the phases at all. And this gives you an indication that maybe you should try rewriting the Hamiltonian in action angle variables, so that you pick apart the magnitude squared and the phases themselves. And then actually something interesting pops out, really evidently, which is that these are all of the trivial resonances here, Stokes and bichromatic waves. Here are the energy exchanges. For each non-trivial energy exchange, say I plus J is K plus L, where these are distinct, right? At least 3 of them are distinct. There's exactly one phase term. This is what we call a dynamic phase for this problem. So the individual phases don't play a role. In fact, for each isolated resonance, say a Benjamin Fair degenerate quartet, there's one phase that controls it. For a type 1a instability, there's one phase that controls it, and so on. So Benjamin Fair, 3 modes, 6 ODEs. I've gotten rid of 2 of those ODEs already. I'll get rid of 2 more momentarily by rewriting the conserved quantities here in a really simple matrix form. So I've got the magnitude squared in here. This is constant, that's constant. These are wave action and momentum. I'm going to pick initial conditions. I'm picking the initial conditions of wave action is equal to the wave action of the Stokes wave, because remember, it's conserved. So going from here to, I'm picking an initial condition corresponding to a Stokes wave on the right-hand side. The matrix here, its kernel is spanned by this vector, which is basically the resonance condition encoded in vector form, and you get a particular solution plus the general solution gives you this thing here. And one amplitude parameter H controls the 3 amplitudes. I'm going to rescale this H in the following way just to get a slightly more elegant system. But the main thing here is we've gone from 6 equations down to 2. I know some of you may be saying, shouldn't we go to 1? The answer is no, and I'll tell you why later on. 1 is worse because 2 gives you a system of ODEs, which is Hamiltonian, and you can analyze everything. You can actually read off everything that you want from the phase plane. So you know, because of the Hamiltonian structure, Jacobian matrix has trace 0. You know that all of the fixed points are going to be centers and saddles only. You know that the linearization is going to be robust. And you're going to map the whole problem. We'll do this on the next slide. You're mapping the whole problem basically onto the surface of a truncated cylinder. Truncated cylinder so here's theta, the dynamic phase variable, and eta, which is energy exchange, going from one mode to the other modes. Say in this case, from carrier to sidebands, but you can also look at other scenarios. So what does the phase plane look like? On the top is where the Stokes waves live. Here I've written in this guy, this is just conservation of wave action. Eta is the first term here. So if eta is equal to 1, that means there are none of the sidebands. All of the energy is in the Stokes wave. That's the top of the phase plane at eta equals 1. And here's the eta variable. At the bottom of the phase plane are the bichromatic waves. So if eta is 0, that's down here, all of the energy is in those bichromatic waves, B and C. That's where they live, here, physical space and Fourier space. In between are trichromatic states and all of the dynamics associated with them. So the typical picture, if you integrate these equations of periodic energy exchange, there it is, right there in the middle. You've got a very simple, I mean, just read it off. In between, you've got fixed points. Well, of course you do, right? You have to have them. They're steady state cases. And actually, these steady state cases have been somehow interesting people recently using somewhat different techniques, but there's quite a lot of interest in these steady state resonant and near resonant cases. They pop out really naturally if you look at the Benjamin Fair instability or the other instabilities in the phase plane. So back to the instability. What does instability, Benjamin Fair instability, mean in this setting? Well, I need to pick two things. I need to pick epsilon, so steepness of the carrier, and mode separation. So say I pick a steepness of epsilon 0.1 right here, and I look at the mode separation P. As I go to P about 0.25 right here, the nullcline at the top of the phase plane stabilizes, so get orbital stability of this nullcline. And this is exactly what my linear stability analysis predicts, right? So stability is really, in this picture, which is the fully nonlinear picture, right? Stability really means, is the nullcline at equals 1 orbitally stable? And you can look at bifurcation, say, with regards to a separation distance P. Here in the inset, there are the sidebands, and you can see how things change as the sidebands move further and further apart. Got some nice bifurcations going on here. Then finally, okay, well, sidebands are separating more and more, and these two fixed points at the top are going to get closer and closer together, finally going to coalesce and disappear. And we see that the trajectories here, the orbits, are basically with almost flat eta. There's not a lot of energy exchange. We're just winding around in the dynamic phase. Yeah. Of course, there's more stuff that you can find if you look for it. And the good thing about the phase plane is it's simple enough that it shows you where to look. So you can find discrete breather solutions, for example. These are just the heteroclinic connections right here. Starting from a fixed point, which is a monochromatic Stokes wave up here. So here's the free surface elevation, and here's the envelope. So I go from monochromatic up there through a modulated plane wave here and back to monochromatic. So this is a kind of discrete Akhmediev breather, which is the first bit. Now it's not exactly Akhmediev because we're in Zakharov equation setting, not NLS. It's the first bit of the Akhmediev breather cycle. And you can compare this with the exact Akhmediev breather solution, by the way. So I've done this here. Solid lines here are the Zakharov equation, dashed are the Akhmediev breather, but only the three modes, the three central modes of the Akhmediev breather. Yeah. And what you see consistently, the Akhmediev breather is always lower here. The carrier depletes more, and the sidebands typically don't saturate as much or don't grow as much. Because in the Akhmediev breather, you start a cascade of this instability that goes out, and it's kind of a pyramidal spectrum or a triangular spectrum. We've only got the start of that process with the initial 3 modes. So you can see where in the NLS, the carrier really can lose basically all of its energy and go and give it to those other modes. For us, the carrier is a bit limited. It can only give to 2 neighbors. You can also play the same game for bifurcation with, say, water depth H. If you're keen to see, and I know the title of the talk said deep water, but if you're keen to see, for example, how the finite depth affects, so this is really KH, it should say at the top. So finite depth, of course, also stabilizes the system. Here we're going to KH 1.363. And analogous results can be obtained for type 1a instabilities, which are instabilities of bichromatic wave trains to bichromatic disturbances, where you're looking at a dynamic phase that has 4 phases in it, and these auxiliary amplitudes. You can do the same for type 1b, which is like Benjamin Fair plus an extra satellite. So here's a Benjamin Fair, and then you add a non-resonant wave. As long as you don't add extra resonances, everything is still planar, right? It's really simple. If you add extra resonances, then you have to be careful. There's also type 2, which you can treat in the same way. So this is like super Benjamin Fair. Got A plus A plus A is B plus C. And it has the same kind of simple description. And you can find type 2 breathers. You can classify the dynamics. And actually, some work on horseshoe instabilities by Schrier, Badulian, and others in the 1990s was going along these lines. So they didn't look at the breathers per se, but they later on they added damping, and they were interested in using this type 2 instability to model crescent water wave patterns. Anyways, the take-home message. How am I with time?
3 or 4 minutes.
Okay, so I can do this at a leisurely pace. The take-home message: isolated quartet and also certain quintet instabilities. So quintet, you lose conservation of wave action. So this is annoying, right? It makes it more difficult to do things. So you could integrate them using Jacobian elliptic functions. But you shouldn't, because then you need to classify roots of these quartic polynomials. And you really, well, maybe some of you are experts at doing this, but I find it really hard to do that. And it's hard to get insight. Whereas it's easier to go one step before and say, I'm going to reduce it to a planar Hamiltonian dynamical system. And then you can identify everything that you want. Periodic orbits, and the fact that energy exchange is happening when the phases are changing, the dynamic phase is changing least, and vice versa. You can find new and explicit breather solutions in the framework of equation. You can break them down algebraically, and you won't capture these using numerical simulations. Because even if you what you think is the breather, you're probably going to end up on a periodic trajectory. So it's difficult to get those if you're just, using Runge-Kutta to integrate. You can easily find the role of these steady state resonant or near resonant waves, so you don't need to use any sophisticated methodology. You can classify instabilities, and there's a little bit more information on this in, well, one paper has appeared, and maybe someday another will. So, thank you very much.